details. And the main part of the paper, in my opinion, is we're suggesting a new parameter of interest, so a new thing to estimate. So I'm not going to be talking too much, partly because we're working out the theoretical details, but partly because the most important thing is the motivation and convincing you that this is a parameter that we want to estimate. This is something that would be useful to know. The next step would then be, okay, how do we estimate it? And what's the most efficient way to estimate it? And we would go down that path. Alrighty, this work is with joint with Ye Luo, who's at University of Hong Kong. And let's start off with a very simple model. So y equals f of x plus epsilon. F, which I'm going to refer to as the regression function, is unknown. We can consider parametric settings where f is known up to a point, such as OLS. And we're also going to be able to accommodate non-parametric settings. So for simplicity, let's just assume that the expect mean independence of the error term, or even just independence of the error term, to make things simple. We're not solving any sort of endogeneity problem in this paper with this technique. It really applies to a broad class of problems, both when you have causality, and it also applies when there's only a predictive interpretation. But it'll make things easier just to focus on a case when there's the causal assumptions hold. And let's also focus where x is one-dimensional for now. It's pretty straightforward to extend the framework to multi-dimensional f, and we'll do that in a couple examples later. And just for the sake of terminology, it'll help me a bit just to view y as a good thing. So more y is better. We're going to talk about a policymaker who's interested in increasing y. So y is good. Just to be very clear about why I say we're interested in estimating f prime, we're interested in the effect of x on y. So the effect, if we increase x by a little bit, how does that affect y? So typically this is done in OLS, and where f prime is just going to be the slope coefficient. We're going to focus on the case where there's possibly non-monotone relationship, either through a parametric polynomial as simple as adding a squared term or in a cubic term, or more generally where we don't even want to impose that type of parametric form. So more generally in terms of non-parametrics. We claim there's an asymmetry between what a lot of models predict and what researchers actually test when they go to testing. And this isn't true for all. There's a lot of papers that, more structural papers, they might use GMM and test the exact parameter that their model makes a prediction about. But a lot of times you'll see predictions from applied theory models that basically suggest monotonicity between two variables. And if you were to talk about a shape between two variables, probably monotonicity is one of the most important ones, or one of the most common ones in economics, especially over the supports where we would observe data, right? So there might be some theoretical satiation point across which, eventually the decreasing marginal returns dominate and there's a decreasing relationship, but in data, the prediction would be that there would be a monotone relationship. And there's a lot of tests of monotonicity that exist, and they're well established. They have very nice theoretical properties. So these are a few of them. Just to point out a couple, there's also still recent work being done. For example, the Chet Verikov and the Feng and Seo 2019 papers. Those tests have nice properties. They have uniform size control. They have they're asymptotically non-conservative, which suggests that they have good power. But few empirical economists apply these tests. We really don't see these tests being used in practice, and that's our big question for motivating the paper we're going to do, is why aren't these tests of monotonicity being used to test what are basically predictions of monotonicity? That's the asymmetry or the gap that we're thinking about. And one answer is that they do their job too well. And by the way, I forgot to mention, I'd be thankful for questions along the way. There's no need to hold them till the end. Yeah, I think this is one of the common cases where it's better to clear up any confusions or get any feedback along the way. So why are tests of monotonicity not used? They do their job too well. They can reject a function from being monotone if there's even a small dip or a small non-monotonicity somewhere. If that's detected, if there's reasonable power, the test of monotonicity will reject because that's what they're structured to do. And that's not what a researcher wants most of the time. So, so why might we have a small non-monotonicity? And there's a lot of reasons. Anyone who's worked with data can probably come up with a lot more reasons. So often you don't have a perfect IID sample. You have a minor amount of selection. You don't have data on the perfect covariates that, according to your theory, you would need to control for. You might have proxy variables. Anything that introduces just a slight bias, measurement error. Anything that introduces a slight bias could cause just a little dip in the estimated regression function. And if that's detected as being a change in the underlying regression function, then that could cause problems. So, and the test of monotonicity would reject, and that's the point, even though the theory might hold for the most part. So, and also the bias might come not because of data issues, it could come from the estimator itself. There's both in parametric settings and in non-parametric settings. In the finite sample, there's often a lot of at least small bias that can happen from tuning parameters, for example, doing a pilot estimation to estimate bandwidth. Anything with more than one stage often is going to have some slight bias. And as we've been learning in economics, I think there's a trend that we're increasingly skeptical of research that is focused only on the p-value. So the p-value is useful for some things, but we don't want to focus too much on it. And I think there's a trend to use, for example, a confidence interval, because that gives you a better idea of the actual effect size. And the current tests of monotonicity, they only give a p-value, and it's hard to interpret that other than the pure test of monotonicity. So if a test rejects monotonicity, there's evidence against against a perfectly monotone function, but we don't know if that evidence is just because of very large power and there's a small dip, or if there's a big dip, a big violation of monotonicity. And similarly, if the test fails to reject monotonicity, that's not evidence that there is monotonicity, right? We know that if it fails, it could be a problem with power, for example, from small sample size, or a large standard error because of highly correlated covariates. So, and now just to make a analogy to OLS, imagine you run OLS in R or Stata or Python, and the results from when you type in your regression are that it gives you back just a p-value that the true coefficient is equal to 0. Suppose it doesn't give you back the actual estimated coefficient, meaning the where you can interpret the magnitude. You can imagine that's not very helpful, just having that p-value, right? It could be very small, just because you have a huge sample size, and the effect could also be very small. So that's the thing we're trying to motivate. And I'd like to just double check, is everything going okay? I want to make sure I didn't get disconnected. Okay, I hear someone turning on their mic.
So yeah, we hear loud and clear. One qualification, the null of monotonicity, I guess, is common to the papers you showed, you mentioned. My doubt back from the econometrics, the econometric I can remember is how precise are these tests on the alternative hypothesis, and what can they or not, what can or cannot they say on functional forms, say convexity, concavity, candidate maxima minima. Is one of the problems, is one of the determinants of the problems you mentioned. These tests are nice, perhaps too nice to be applied. The fact that when you reject monotonicity, there may be too much going on in the alternative. And so these tests are too little applicable in a way, operationalizable.
Yeah, that's a good question. So first of all, these tests can handle, at least for example, Feng and CO 2019, that can handle convexity. The other papers I think are mostly focused on monotonicity. In terms of the alternative, yes, so they're really only for monotonicity, and yes, the functional form. So they assume that they do allow for non-parametric, so you don't have to specify the functional form. So really, they reject if they find any sort of non-monotonicity in the underlying regression function. So the estimate, if you were to just show a scatter plot and do a non-parametric estimate through it, it might have a non-monotone part. It might wiggle a little bit. That doesn't necessarily mean that the test will reject. So the tests do differentiate between, the non-parametric estimate and the idea that it might just be statistical noise coming from the epsilon term. So they do look for parts where there's a significant dip, but that could be just because there's a lot of points and there's a significant dip in 1% of the data points. I'm not sure if I answered your question. Is that what you were getting at?
100%. Yeah.
Okay.
Thanks.
Great.
Thanks for pointing out.
Thank you for the question. Great. So so this is what they give. I want to be clear with what I mean by test statistic that is hard to interpret. So if you understand the slide, it's actually going to go against my point. So don't try too hard to parse what the slide is doing. You can skip to the last line, which says the test consists of rejecting H0 if the value of this test statistic, Tm, is too large. So this is how most of the tests of monotonicity are structured. They have this creative, and this paper is very good, by the way, and this test has nice properties. And so the tests are structured to, they have this creative test statistic that captures monotonicity in some way. And they just reject if that test statistic is large, and they give back a p-value, right? The actual test statistic, this Tm here, is not the primary object of interest. It's just an intermediary to get a p-value. So, and a lot of this is what I mean by test statistics are difficult to interpret in the current tests of monotonicity. So the point of this slide is not for you to. If you do understand it, then that actually goes against my point. Alrighty, so what's the solution? You can probably see where I'm going. The solution is to estimate a parameter, make a test based on a test statistic that is interpretable. And we think this is important. Just in general, we think this is an important goal, and it is recognized by others as an important goal. It's often just not feasible or too difficult. But in our setting, we think it is feasible. And it's important to do this because often assumptions don't hold exactly. Often you're going to have some bias. And the key is that if there's a small amount of bias, or if in econometrics, one thing when we teach, we basically say at some point, in all cases, some assumption is violent, right? Whether it's the assumption that we have an infinite sample size, right, that asymptotics hold. So it's good to have a technique that is continuous in some sense in the violation of the monotonicity, right? So for example, OLS, we know that even if the relationship is not linear, we still get something useful out of OLS. We still get the best, in some sense of the word, linear approximation, which often is what we want. So we're looking for something similar in the context of monotonicity. And we also want to have a confidence interval for the parameter, so we can see whether predictions for the theory hold for the most part. So even if we reject pure monotonicity. So basically, we're not going...
Scott, excuse me?
Please.
We are wondering, do you have an example? Did you do a simulation or a real example where this problem is important? Explaining when you are going to find this problem, estimating any function. You know what I mean?
Yeah, I know what you mean. An example in terms of showing that the tests of monotonicity actually do reject when you have a small...
A real example where, for example, if you are looking at the relationship between the price of a good and the demand, for example, you know what a real example, an actual example where you can see this is a big problem.
Yes, yeah. Good question.
You are just focusing on the theoretical part, or any empirical example where this is important?
Yes, I'm going to discuss examples, but I'm just going to walk through them. I'm not going to show, I'm only going to have one part where I show I'm only going to have one slide where I show actual results. We're still working on implementing the estimator, but I think I can satisfy some of your concern by just talking about actual real examples in economics. So I will talk about production functions. I will talk about I'll have a slide where I talk about angle curves. Okay. But today I don't have a large empirical section. Okay. Yeah, but I will move a little bit more away from the abstract towards some more concrete examples.
Okay. Go ahead. Thank you.
Yeah, thank you. Yeah, we definitely need to explore. We're going to explore some empirical cases, but we haven't gotten that far yet. Okay, so this is the parameter that we're looking at. This is the partial monotonicity parameter, and you can see that we define it to be this delta plus, which equals the probability that f prime of x is greater than 0. And one of the advantages of this parameter is that it's equal to it's very easy to interpret, right? It's the proportion of the population for which increasing the x variable is beneficial. Remember, I said we're going to interpret a larger y as something desired, something good. So in other words, it's the proportion of the population for which increasing x marginally increases also the y value. And alternatively, you can interpret it as if you take someone at random from the population and you increase their x by a small amount, it's the probability that person's y value will also increase by a small amount. So this is the parameter that we're going to study. This is the parameter that we propose as a parameter of interest. So you can imagine that if this value is 1, and I'm going to show this shortly, this corresponds to pure monotonicity, right? This corresponds to pure. Let me show you graphically how this works. So this is a function that is mostly increasing, but there is a small part where it's over which it's decreasing, and that's colored in red, and it has the shaded region. So the partial monotonicity parameter in this case is 0.875, which just reflects that the function is mostly increasing. But obviously this would be rejected by a test of monotonicity, since that only picks up when the parameter is equal to 1. I'm going to get to examples in 1 or 2 slides, or probably in 2 or 3 slides. So I'm almost there though. But I see I should start with the examples earlier. So thank you for that. So we can make hypothesis tests based on PMP for two special cases. So basically this slide shows that we can use PMP to do a test of pure monotonicity. So that just corresponds to the delta plus equaling 1. So we can actually carry out this test just like, and we can compare it to the tests of regression monotonicity. And one more point before examples. So with a PMP, the key thing is we can make a confidence interval. So suppose we reject monotonicity. Well, with a PMP, we can look at the confidence interval. If it's large, if it's centered close to 1, that means there's a lot of evidence supporting monotonicity to a large extent, even though the value 1 would be rejected. You can imagine a confidence interval 0.9 to 0.95. So the key thing is we can make a confidence interval because we have a parameter of interest. And this is some related literature. I think I'm going to skip it. Basically it falls in, it also recognizes heterogeneous effects, the idea that increasing X might decrease in some parts and increase in other parts, but they focus more on the average derivative, the average effect. And PMP focuses just on the average sign of the effect. So you can imagine OLS. OLS is an average effect estimator. And we're not trying to replace that. We're not suggesting PMP should be used instead of that. We're suggesting that they can be complementary. They both pick up different things. So the PMP picks up only whether the effect is positive or negative, and the OLS, or the average effect estimator, picks up more about the sign of the effect. All right, example. So production functions. Suppose we want to test some simple facts about a regression function. And again, if you actually get data from a regression function, and we're working on this. We have data on a regression function. We're implementing the tests for this. We just don't have them available yet. So often you'll reject econometric economic axioms that we assume hold. For example, even monotonicity, that more of an input leads to more of an output. You can often reject that case. And just because of what I mentioned before, data issues, you don't necessarily have an IID sample. The producers are often different in very important ways, meaning those that have a lot of the input might be inefficient in some other term. That's why they need a lot of input. So that's why it's important to have these partial parameters that will show you to what extent monotonicity holds, monotonicity in the inputs. And similarly, you can imagine you might want to look at over what proportion of the support do you have increasing returns in a production function. And a final point 3, we can talk about complements. So complements are typically defined as either 0 or 1. Two inputs are either complements or they're not complements. But in practice, it's useful to be able to talk about them being complements to a large extent.
A question, Scott. In the slides, there are small L and K and large L and K. Mm-hmm. Is there any difference between them, or is the same?
Thank you for the question. Yes. So the small L and K are just the function argument. So since this is a bivariate production function, you can imagine the small L and K are the true, are just the grid points over which we can imagine the function. They're just the kind of the dummy functions to the argument. The large L and K are actually drawn from the population. So they're random variables. And that's what makes the probability statement a probability statement. So I'm glad you asked that question, since I need to be more clear about that. This measure, PMP, basically integrates over the marginal density of the X variables, which in this case are the labor and the capital. So imagine you have an industry where you can imagine a rectangular grid. So L and K take values from 0 to 100 each. but they're probably positively correlated, right? In industries where you have lots of labor, you also have lots of capital. And so in practice, you would see a marginal density that is concentrated on the diagonal. So they pick up basically, let me go back here. I think this will be, explain my point more clearly. Here in this example, we're assuming a uniform distribution. Now, if instead we have a for the x variable, right? If instead we have a distribution that is concentrated on values before the red part, then the partial monotonicity parameter could be close to 1, or actually it would be 1, because we don't observe any values in the data around the red part. So the partial monotonicity parameter actually captures that we might not have any observations close to the red part. So if you increase the x value in the data, the y value would increase. So that's what the capital X and the capital L and K capture are. It captures that we're weighting, in some sense, our measure with respect to the actual distribution that we're applying it to. Does that answer your question?
Sure, yes.
Okay, thank you. Great. So this is our example for production functions. And now we're going to go the opposite way from what I just suggested. And we might actually, so let's suppose we have a prediction about the life cycle, in which case our x variable would be age and y is the outcome of interest. For example, it could be consumption, where I saw a paper recently on consumption inequality with respect to age. It could be savings. And you often see predictions that the shape of a particular regression function over the life cycle takes a certain form. For example, monotonicity or convexity. Just to give an example, I just saw a recent paper that discusses how consumption inequality is monotone with respect to age, meaning if you define inequality in terms of consumption, it increases as a function of age. This paper was arguing in that setting. So that's a prediction of monotonicity. Now, in this setting, we actually don't want to do that weighting that I suggested. We don't want to weight with respect to age. Age probably has a distribution that is heavily skewed towards the first part of the regression. That's skewed towards lower ages, right? In many populations, you don't observe a lot of observations at high ages. But the prediction often makes a prediction about how things behave at high ages. And probably that should be tested in the same way, given just as much weight as testing for the earlier ages. So here we can actually define a different related parameter, PMP, that is not weighted. Okay, so in other words, it takes the uniform distribution. Another example, which I alluded to earlier, is in any intervention or any policy implication, almost all the papers that we see out there are focused on testing that the average effect is positive. But we know that if we only focus on the average effect, we can get into trouble. So we know that OLS has the possibility of, if there's if there's a large effect for a minority, that could lead to an average effect that's positive, even if for the majority of the population, the policy would be harmful. So this is a little subjective when I say that policymakers should be interested in this, but you can imagine that some policymakers would be interested in, a policy that they might have a criteria that it's beneficial for the majority of the population and the average effect is positive. Okay, so PMP and OLS can be combined in this way. You can make statements about the average effect and the monotonicity. And let's talk about another example, which we're going to talk about a binary treatment example. We can extend this to a continuous treatment, but it's more simple just to think about in terms of binary. So suppose we observe an outcome variable before and after treatment, And we want to explore the heterogeneity of the treatment variable. So suppose there's a drug or a vaccine or whatever it may be, that the effectiveness of it, or basically whether it is effective, depends on someone's age or their weight or their blood pressure, right? There's heterogeneous effects. And we can explore that. So we can capture those as a function of z. So basically, if f of z is positive, that means there was a positive, there was a good, if the drug was effective or the intervention was effective. And so we can define a partial monotonicity parameter that just picks up for what proportion of the population is that the case. Now, I want to talk about, we allow for non-parametric estimation, meaning full without specifying f. But in practice, we're usually more interested in semi-parametric estimation, right? We want to control for lots of variables. And again, this is a technique we want people to actually use. And in practice, you often have 100 covariates. Well, you can still estimate the PMP controlling for 100 covariates in many cases using either partial linear models where we capture most of the effects linearly, but we allow for the effect of the variable of interest to be captured in a without specifying the functional form. And we also allow for generalized additive models, which are a great semi-parametric tool that they're feasible because it's additive. That's the key part that makes them not non-parametric. And it allows for us, we don't have to specify the FJ, the functional forms of the FJ. So both of those, so we can embed this framework of PMP into very practical estimation methods. So, and let's take a sort of a different approach. Suppose the researcher wants to test that a monotone relationship between two other variables, y and x, is driven by something else. And we can do that by basically doing the approach that is commonly taken with average effects. So often you'll see researchers show a regression table where they show the effect, meaning basically just regressing on x, and then they break down that effect by controlling for covariates. And that's how you can kind of see the channels of how the effect works. And you can do the same thing. The PMP allows us to do the same thing in the context of monotonicity. And I'm going to give an empirical example, at least a short one, next. So let's suppose we are regressing life satisfaction on age. So life satisfaction is the variable, how satisfied are you with your life as a whole these days? Be very interesting to see these results recently over the last few months. And from a scale from 1 to 10. So again, larger values are better. And if we just regress life satisfaction on age, just with OLS, we get the following results. A minus 0.0022. Now that's very small, right? Even though age goes from 0 to more than 100, that's not a large effect considering the range of life satisfaction is from 1 to 10. Now, immediately you can see that PMP is useful here. It comes back as 0.33, which means that the relationship is only increasing over 33% of the observed relationship. And so that means it's decreasing over a lot. In other words, it tells us right away our functional form for OLS is not correct. And this is kind of another use for PMP. It can give you hints on the functional form, meaning we should add a squared term or a cubic term, or we should consider non-parametric regression. And another key thing with this is we're able to understand something very complex with just a few numbers. And that's one of the reasons why we think that PMP might be used by people, hopefully, is because it has those advantages of OLS, of being able to represent things with just a few numbers. Now, let's look what happens when we control for a third variable, financial satisfaction. And you can see that the coefficients on age, it stays mostly the same. But the key thing is that the PMP decreases. So it's close to zero, meaning there's actually a decreasing relationship between life satisfaction and age once we control for financial satisfaction. In other words, financial satisfaction was what was driving the monotone increasing part of age when we were not controlling for financial satisfaction. And it'd be better to see these graphically, but the point is we can get this story from just this table of 12 numbers. And so you can imagine that PMP can do the same thing OLS does in those typical tables where you have one regression per column. So there are semi-parametric methods that give you a graph for each coefficient, but doing that in the same way that you use OLS and show so many results is not feasible. So unfortunately, this is the only empirical slide of the paper. We're working on doing several applications, and we hope to make progress on that soon. So more applications to think of, angle curves. So this kind of goes along the lines of the partial complements or the partial increasing returns that we were talking about with example 1. Often a good is classified as either normal or inferior, but in practice we might think that
Scott?
Yes.
Another question is there any relationship between the delta PMP and the R square of the regression? Because
that's a good,
it should be, if you look at the R square of the first regression, maybe there is a relation. That is the point. Maybe there should be a relationship between delta and the R square. So
that's a very good point. Yes, I agree. And actually, I should list the R squared there. I absolutely should give the R squared. I'm going to make a note of that. Thank you. Yes, there is a relationship, and the R squared captures the fit as a whole. And so well, one difference is the PMP only captures the sign of the sign. So it could be that the relationship, it could be that F is nonlinear, but increasing. Okay. And the PMP would not capture that. The R squared would capture that because the R squared is looking at the distance between the line and this curve, whereas the PMP just indicates that we're not capturing the sign. So the PMP really is focused on monotonicity, whereas the R squared picks up something more general of whether the functional form is also correct. So in that sense, the R squared picks up something more general. And another related point to that is that the PMP picks up kind of a goodness of fit for one variable. So the R squared, if you have many variables, you can imagine, in this case, we only have one control variable, but you can imagine 10 control variables and we add another control variable, it might increase the R squared slightly, but the PMP can capture whether even for a variable that doesn't have a lot of explanatory power, a lot of times we have experiments, for example, where the treatment actually doesn't have a high R squared. If you imagine increasing someone's income, if you give some people randomly $100 and some people not $100 and their outcome is their total income, that's not going to have a high R squared. So the PMP can capture the relationship even when there's not a lot of explanatory power of the variable. But to go back to your initial point, I should list the R squared. So thank you for that that point. That would be helpful information.
Okay, no, maybe the difference can be PMP capture only monotonicity, and the R square, you can have a small R square, not only because it's no monotone, just but also because it's non-linear. Yeah. Might be the difference there. It's non-linearity. The R square is low because non-linearity and non-monotonicity and this is just because of non-monotonicity. So that is, but our relationship should be, and I think it would be to solve the paper. It would be interesting to the difference.
Yeah, I think that's a good point, and yeah, I agree. We should motivate that better. So I think one way to kind of motivate that is that when we use OLS, we accept that things aren't perfectly linear, right? We don't we know that assumption is probably false, and so the R squared does capture that, but we're kind of basically claiming that if not only it's nonlinear but it's non-monotone, that's something that we might be concerned about. That depends on the particular application, but that's a good point. We should make some.
And also, the point here is I don't see how useful is this point, because, for example, in a linear model you can include non-linear variables. Parabol, I don't know, a square relationship, if y equal x squared, is you can capture the relationship with this non-linear relationship in a linear regression model. So that is the point. So there are, to me, it's difficult to see how important is this issue when we are estimating a model. Maybe so that is, I don't see how important it is, but that is to motivate to look for the sample, and I stop talking because it's not my talk. Okay, thank you.
Thank you very much for that critique. I appreciate that. And yes, I agree. To a large extent, we can add polynomial terms and we can capture a nonlinear relationship using OLS. And actually, we can estimate PMP using OLS. So we can use OLS. But if you just throw in there's a few issues. One, when I see researchers add polynomial terms, often it's in an ad hoc way, meaning they just add a couple or they just add a square term, or they add a cubic term, or they add it according to some criterion, for example, the BIC or the AIC, or the adjusted R squared. But that criterion is for measuring whether the fit of the average effect is a good fit. It's not focused on whether the sign is a good fit. So PMP does that. And also, it's hard to interpret. Once you add these polynomial terms, you can interpret it by showing a graph. But especially if you want to show a table with many results, it's pretty difficult to interpret even a square term actually in your head to kind of back out, okay, where's the minimum, and it's decreasing before that. So it's very hard to interpret. I should show some points on that, because that's obviously an important line of motivation that we should take. And finally, I would say that one of the big contributions of this paper is that we make it work in non-parametric settings. So in that sense, it's nice to be able to do that without putting, choosing polynomials. But I need to show an example where if you do it this way, you get a misleading conclusion, whereas if you use this new technique that we're suggesting, you get the right thing. I need to give a clear example where that's the case to make that point. So I accept your critique. Yeah, I think that's a good point. Okay, let me make yes.
The last point is, I am a financial econometric guy, so in finance you have a lot of examples where you have asymmetric behavior in the upper tail and the lower tail, so non-monotone relationships. So you are going to find thousands of samples in finance with non-monotone relationships. So in that case, I think you can find good example for your work. Okay.
Thank you. That's a very good point. So you said where specifically there's non-monotonicity, either in the tails you're talking about?
Yeah.
Okay.
The relationship between two assets, you have different behavior on the upper tail than in the lower tail. You know what I mean? The relationship maybe in the upper tail can be positive or negative, and the lower tail you have a negative or positive relationship. So there is no monotone relationship along the full distribution or the whole distribution, the joint distribution.
And so, what's the specific? Is it the price of the asset?
Returns.
Okay, returns. Okay, thank you. I'll look into that. That sounds like a very helpful example. Yeah, thank you. Great. Yes, this is very helpful critiques and advice. I really appreciate this. Okay, let me just do a couple more slides, and I think I can conclude soon. So angle curves is another example. I already talked about that. We might want to talk about that a good is 80% normal or 80% inferior, meaning not just 0 or 1. We're still working on theoretical results, and I don't think I need to go into details at that point. We're basically going to prove that the bootstrap works in a wide range of parametric models, and also for a specific non-parametric model. For example, nonlinear local linear estimation. This slide, I've talked about a lot of these properties already. It's nice that delta plus is unit free, so it kind of shares correlation, as it shares that nice property with correlation. And another nice property is that the parameter space of delta plus, even if you use a multivariate, even non-parametric model, delta plus still has easy to represent parameter space. It's just a unit interval from 0 to 1. So it's very manageable. Usually in non-parametrics, the parameter space increases as the dimension of the underlying function increases. And that's not the case here. And we have some extensions we want to explore, partly that incorporate magnitudes or that incorporate non-marginal increases. So for example, if we increase income by $1,000, that wouldn't be viewed as a marginal increase. So we would want to look at that particular relationship. And I think I can skip these couple slides. I talked about this. We already talked about, I'll talk about this a little bit. We talked about the R squared. And so the delta plus, the PMP, can be viewed as kind of focusing on the fit of the actual variable of interest, even if it doesn't have a high explanatory power. But we should do a numerical example with this that should show this point. So finally, in conclusion, we think that PMP could just be a helpful tool that empirical researchers can add to their toolbox. Especially, it doesn't have to be corresponding to when there's an underlying prediction of monotonicity. Often, especially in reduced form, or we don't have an underlying relationship that we want to test. We just want to ask the data, what's your average effect? And we want to get an idea, is it monotone? And it's interesting, researchers often want to think about the parts where it's not monotone. Usually something strange is going on, and it's important to explain why a relationship is not monotone for that particular subgroup. And we think this could be interesting to policymakers, just because it captures more the idea of, is something beneficial or not, abstracting away from the actual magnitude of the effect. And again, we think that the PMP can be complementary. We're not trying to substitute OLS. Alrighty, and that's it. That's all I have for today. Thank you very much for your comments. I already see several things that we need to improve about the presentation, also incorporate into the motivation of the paper. So thank you for that. That's exactly what I was hoping for. So I appreciate that feedback.
Okay, thank you very much, Scott. I think that we still have some time for some questions. Marcelo, are you still around? Marcelo is not around.
May I ask one question?
Okay, Andres, go ahead.
Okay, so thank you very much for the presentation. Very nice, very clear. I have just it's more a comment than a question. Maybe you could think of an application on instrumental variable estimation, right? Because in the first stage, you need monotonicity of the instrument, and sometimes this is suspicious that is not satisfied, or maybe is not satisfied because a small subset of individuals. So probably it would help to improve and refine the instrument used in the first stage, right? So I would say it would be a nice application of the PMP.
Thank you. That seems like a good idea. So you're talking about the monotonicity assumption, right? Of the instrument, that the instrument basically pushes people one way or the other way.
Exactly.
Right. Is that, do you happen to know of a particular one where we can actually estimate that? Because don't we need to know the counterfactual for that? We need to know what would have happened if they had a different value for the instrument.
Yeah, but they have different values for the instrument, right? I mean, you have the instrument for everybody. Then some people with, I mean, you have these compliers, which are those individuals that actually are monotonous in the sense that they get higher X, higher noise variable when the instrument is larger, right? And then you have these other individuals that actually you are not identifying the effect for them, which are either always takers, never takers, or the defiers that are the problematic ones, because the defiers are those that, let's say, make the IV not to work. So you could, let's say, identify the defiers with your method, I think.
Okay, so basically, as long as the heterogeneity is observed, meaning there's the variable that determine. I see what you're. That's a good idea. Yeah, I agree. That's important, and that's important in a lot of settings. So,
exactly.
Yeah, thank you for that. I'm going to look into that.
Hi, Scott. I'm Luis. I'm a theorist, but I would like to know more about how the complement to other possibilities testing this monotonicity, how your paper complements this. So do you have an idea in which or kind of field in which the current tests are a little bit dubious and you can actually improve with your tests, something like this? I think this would add a lot to the value of the paper, right?
Yeah. So the current tests of monotonicity, it really depends on what the researcher wants. If the researcher or the theorist wants to test pure monotonicity, meaning they want the test to reject if there's a small violation of monotonicity, then I think that the current tests of monotonicity are very good and very adequate. The only advantage that PMP has over those tests in that case where you do want to test pure monotonicity is in terms of the power. So if a test of monotonicity fails to reject, it's hard to figure out whether that, let's say a test of let's say that it fails to reject. It's hard to figure out whether it fails to reject because it's low power or because the function is monotone. And so you can do a power analysis, but to do a power analysis, you have to choose an element from the alternative set to generate the power analysis. Whereas for PMP, you can look at the confidence interval. So if the confidence interval is closely centered around 1, if it's 0.99 to 1, that's strong evidence that the regression function is monotone, meaning it's not a question of power. Other than that, I would say the main motivation is for when you don't want the test to reject when there's not pure monotonicity. So, and that is field specific. It might depend on the actual theory that's being tested. But yeah, we should motivate that and think more specifically about the different areas. Great, thank you, Luis.
Okay. So, any more questions? Yes, no? Well, thank you, Scott. I think that your presentation was great, very clarifying. I hope that this early session for you was worth the effort.
Absolutely. Thank you. I really appreciate the comments, and thank you for all of your time.
Okay,
I really appreciate it.
Scott, thank you very much. You did a very good job with your presentation, very clear, and that is why it raised a lot of questions. So thank you very much.
Okay, so it's time.
Thank you.
It's time for an ovation.
Thank
Okay,
you.
thanks a lot.
Okay,
Okay,
guys.
thanks a lot, Scott. It was great.
Thank you. Thank you.